Hi, everybody. Thanks for coming in. It's real hot. I'm Jason Perry. I'm the Director of Utility and Energy Management at the University of Georgia. And Ben, you want to quickly introduce yourself?
Ben Dombrowski, Energy Planning Specialist for Jacobs.
And we're going to talk about a project that for me has been ongoing for almost 3 years now. In fact, I started this project as the campus energy engineer, and now I'm the director of the department. So it worked out pretty good for me, I think. So almost 3 years ago, I was tasked as the campus energy engineer to start scoping a utility master plan by my leadership. And so I began the process of facilitating stakeholder input sessions with anyone who touches utilities at UGA. And ultimately, we developed a scope that we put out for proposals, and Jacobs won the selection. And what we wanted was basically a two-parter. So we wanted a warts and all facility condition assessment, as well as a plan looking at the next 10 to 30 years for developing utilities that made sense and put us on a path with plan and purpose. And so I don't show it here, but what I drew was kind of a wedge. So narrow end now and growing wider as time goes on, because you can never really plan. What we didn't want is a path, just a single path that says do this, 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 and this, because once you get out to here, it's really blurry. And anybody from a university here? Yeah, okay. You probably know what that's like, is things change really quickly. So there's arguments over who is the oldest public university in the United States. UGA has claimed, as do two other universities. We were chartered in 1785, but didn't hold classes till 1800. So we have buildings that are over 200 years old. We have some that are in construction now. And through all of that, we've had a central steam plant since the 1920s. That has grown tremendously to 7 miles of distribution now from our central plant. While we do have a physical master plan, it is separate from the utility master plan, and it says where things may go, but it doesn't say when. And because project timing is, as a state institution, tends to be political or due to imminent demand, such as we need a new dorm because enrollment has exceeded our capacity, things like that. And so as a result, we tend to be in a reactive mode when it comes to utilities. So we build 5 new buildings and then suddenly realize that the circuits feeding them from our substation are under capacity at that point, or have reached capacity at that point. Same thing with chilled water, same thing. Well, steam, we're never running out of capacity, but it's a different story. So the primary desire for this master plan was to move from a reactive stance to a proactive stance, and everybody can appreciate that, I hope. And so, working within the unpredictable timelines of construction and renovation projects, we wanted to be in a position to be able to say, yes, there's enough chilled water capacity in this area, you want to build a new dorm, or no, but here's what we need to do to get to that place. Rather than scrambling to figure out if on paper we have enough chilled water firm capacity in the Southwest District or something like that. As part of this scoping project that I did before we brought Jacobs on board, I sat down facilities leadership, I sat down campus planners, the steam system folks, chilled water folks, electrical folks, and I asked them questions like, what do you wish they had planned for 30 years ago? What would be the worst thing to happen? What would be the best thing to happen through this process? And so some of the things that came out were, we kind of categorized into guiding principles. One of the ones that's sort of a sleeper here is the bottom left corner, is eliminate the concept of waste heat. And you can read the rest of that, but hopefully that makes sense to you. And then, of course, the title of this presentation is Leveraging Golden Opportunities. So We threw that in there as really initially just saying, like, let's not dig twice if we don't have to. Let's put in things in the ground once and not have to disrupt campus too much. But it led to a whole lot more of a mentality as the process went on. And then these are the broader priorities, so the folks who have more of a pedagogical purview in facilities, which is our sustainability office, brought in the mission to the university. So Campus as a Living Lab may resonate with those of you from other universities. That's something that's really important to us, using the campus facilities as a teaching and learning opportunity and research opportunity as well. And a bit more about the why. So in recent years, you can see our fiscal year 21 to FY 25 projected, which is almost over. Our fiscal year ends in June. Our total utility spend has increased 64% in just that short period of time, most of which is driven by electricity costs. And we buy electricity for the main campus, as well as a few other facilities on a real-time price basis. I assume most of you are familiar with that concept, but the top chart shows our calendar year 2024 hourly incremental electricity cost. That one on the left is in January, and that's the most expensive hour was $73,000 for 1 hour of marginal cost of electricity. And then, of course, the summertime is more sustained but lower hourly costs. And if you sort those all from highest to lowest, there are 300 hours that were responsible for half of our incremental cost and a fifth of the total bill. So some trends in higher education utilities. Steam, broadly speaking, is no longer the preferred heating medium. That's not universally true. Talking with our colleagues or counterparts at Cornell, who have been proactively investing in their steam distribution and production systems, they're not in a position to say, hey, let's just convert to hot water distribution instead, whereas we're in a position to start evaluating that. Resiliency has become non-negotiable and not only has fiscal impacts, but also reputational impacts. So we've had a number of recent minor but visible outages at our substation caused by critters. We had a raccoon just commit suicide in our substation and knocked out a circuit for a few hours. Nothing totally catastrophic, but now the president's office is asking, like, what are we doing about electrical resiliency? I'm like, so glad you asked. Here are all the things we need. And then, of course, new generations are driving sustainability. If you look at a number of different studies, new undergrads are using sustainability as a filtering tool to determine where they would like to go to school. So our existing conditions, I mentioned that we have 7 miles of steam and condensate distribution. Our qualitative analysis of the efficiency from gas meter at the steam plant to end use to condensate return is around 34%. And then, best in class would be 50 to 60%. We have sections of steam distribution and condensate distribution or return that we don't know how old it is. That's how old it is. Nobody's around to know. And there are no drawings for it. Lots of maintenance. Steam, when you stand back and squint at it, is a beautifully elegant system that, you boil water and under pressure at the lowest point on your campus, it kind of magically goes uphill. You use the energy from it, it flows back downhill. But when you get into the nitty-gritty, of course, you've got traps and you've got, all kinds of different fiddly bits that are dangerous and hard to get at and require a lot of maintenance. And then the lack of flexibility, going back to that need or desire to eliminate the concept of waste heat, it's not impossible, but not exactly off the shelf to capture waste heat from another process to turn into steam. Chilled water. So we have 6 distinct chilled water districts on campus, 2 of which have centralized district energy plants. The rest are chillers in buildings that are looped to each other. We have 76 different chiller systems in total that spread our staff over many, many acres of campus. And of course, the opportunities of centralization are fairly obvious. And that's the mode that we're going towards. It started, I think our first DEP was in 2010, so it's not that new to us in the grand scheme of things. It's the direction we would like to go. But finding locations to put DEPs, as we were just discussing before we started, is continuing to be a process of convincing architects that, yeah, you actually need to dedicate that spot for this instead of the shiny new thing you wanted. And then the electrical system, we have a single substation that serves our main campus. About 90% of our electricity that we buy in the Athens area goes through this one location. So it's obviously a single point of failure. It is, we have 21 circuits, and so many of those are at or near capacity. We've recently derated the calculation for our ampacity. I am a mechanical engineer. I'm going to mess some of this up, sorry. But during hot weather, when circuits are constrained and heavily loaded, we don't have a lot of flexibility to reconnect a circuit to a different bank in the substation if there were an outage or a reason to do maintenance during that time. And so right now we're actually about to sign the paperwork on increasing the capacity of the third bank of 3 that have, the other 2 have been upgraded from 25 MVA to 40. The third one was not done due to finance constraints, and so we're about to do that now.
So I'll go ahead and talk about some of the thermal solutions we evaluated and what we came to. And since I'm not as smart as Jason and don't have a cool beard, I'm going to kind of give you some 3 takeaways first at a high level and then dive into some of those details. So the first thing that was really key is the leveraging of data and gaining the value out of that data. And that's kind of a thing that goes across whether you're planning or if you're using CXL or anything, not just putting it in to make your job easier, but how can you extract that value? Luckily with UGA, we had great data, whether it's plans, meter data, access into their control system. All that data was really useful, and we tried to really drive that value into the solutions we looked at. Another thing is, as we start to look at different things in the energy world, it's quickly evolving, right? VFDs on chillers are now kind of standard practice. There's been the coming and going of hydrogen. Heat pumps, no one is really talking too much about them. Now they're the go-to solution for a lot of these different things overall. So I always challenge, since we're able to look at things a little quicker with all the data we have access to, try to open up your idea and look at it a little bit and revisit something that maybe not 5 years ago worked, but now is the prime solution for that. And then finally, with all this data that we're using and all these solutions that we're working towards, the need for that kind of accuracy of that data, as we start to look at heat recovery and the kind of understanding of that, it's really important that we kind of nail that down correctly so we can accurately portray what's going to happen. So just those kind of takeaways are really important no matter what you're doing and how you leverage that information in a meaningful way. So for the master plan at UGA, what we kind of did is it took that approach in the 3-stage approach overall and how we looked at things. We looked at a wide variety of solutions early on and kind of see how they would fit on campus. And then we worked to narrow that down, doing a more detailed life cycle cost analysis, getting that full, big, holistic picture, understanding not only how it operates at a district level, but impacts the buildings and all of that overall. And really understand how that looks, not just today, but 30 years from now. And then finally, we worked really hard to get to that implementation solution so that we have defined projects, discrete projects that they can move forward with action. And that's really important out of our clients. Again, whether it's a plan or commissioning, you really want to make sure there's actionable items that you come out with. And that's something that we really try to focus on through this process. So to really look at it, there's a long list of things. Here's just kind of a sample of what we started with as we looked at these elements and things that we thought would pan out. Like CHP didn't end up really valuable as we look forward, but other things that we started to begin to explore, like heat pump chillers, wastewater exchange, ambient loops, those became very interesting. So things that we initially thought we were going to wave off, but then we dove into that data and those details, and it started to look very interesting from that perspective. So with that, we brought forward a bunch of different scenarios that we looked at for the university and did that a full kind of life cycle cost, but also understanding what is the sustainability impact? What is the ability to actually deploy this? Like, how much of an impact does it have on campus? What is the initial capital investment? Is that truly feasible? What does it do to the resiliency? Is it really enhancing resiliency, or is it no change? Is it maintainable too, right? We have a steam system that we're looking at, and if we're trying to change over to hot water, we have to operate two systems at the same time. Is that something that we can maintain with the long-term future? So one of the tools that we utilized to do this was our virtual infrastructure software, purpose-built for master planning, and really focused in on that holistic view of different things. So we were able to take all the information, all that data that I just talked about, at the building level, at the plant level, at the distribution level, and threw it all into this simulation software to model what the output actually looks like, understand, again, that resiliency, sustainability, as well as the cost, and line out the different projects that we had to do with that, so we get a true understanding of what that looks like. And we bring into those, as Jason mentioned, the buildings, their ideas of where they could be and what the size could be. So we also kind of understood and had that flexibility to look at different what-if situations of when a building was going to go here or there and move things around very quickly to understand what that looked like. So then finally what we ended up with was two scenarios, a kind of a more efficient scenario that we'll get to in a little bit, and then a conversion over to chilled water, hot water. And with that, we focused again in on the actions, how we implement this. Ultimately, how can we get these actionable projects, these discrete projects within the funding sources that are available to the university to make sure that this moves forward. And we kind of work in a way that we consider the deferred maintenance as well, right? Like, we want to be able to, as Jason mentioned before, seek those golden opportunities. Instead of replacing a chiller like for like, can we now weave it into the long-term plan as we move forward? So that was another goal of it. What we ended up coming up with the preferred solution was Jason termed optimal resource utilization scenario, was a energy exchange solution with an energy spine. So UGA had the fortunate opportunity of procuring a railroad that went right down the middle of their campus. So there's no, as anyone that's worked with the railroad, there's no utilities there. They don't let anything go through or under them ever. So it's this kind of fresh area that we could put in new energy to. And instead of just running chilled water and hot water, we used it as a kind of ambient loop exchange to be able to capture energy, whether it's heat or cooling, from different district energy plants that they have located throughout the campus, and utilize it in other areas of the campus. So it really was an efficient way for us to capture that waste heat or that excess energy and put it in a meaningful way. And additionally, we were able to tie in, they're also right next to a wastewater treatment plant, so being able to utilize the sanitary heat, recover that thermal energy from there, as well as you see down at the south part of the drawing, a geothermal well field that will go in the intramural field space overall. So really kind of what we were able to do is really leverage the resources that we had in a good, meaningful way without trying to disrupt campus or minimize our disruption to campus.
If I could just interject, I don't know if you've ever sat in a room with all of the technical stakeholders in a facilities group at a university when they all go, yeah. That's what happened when they presented this. It was really transformational to watch that.
Yeah, it was a really cool moment to be able to have that, everyone just nodding their head. It was amazing. So the outcome associated with that, not only we were kind of really transforming their campus in a large way and redoing a lot of their infrastructure, but ultimately what we're able to do is reduce their total lifecycle cost down by approximately 30% compared to the business as usual case. In addition, we were able to reduce the energy that the district energy system was using by 60%. So not only were we driving down lifecycle cost, we were really reducing their energy, as well as enhancing their resiliency, removing some of the deferred maintenance that existed overall. So really tried to, like I said, kind of came together with this golden opportunity for the system and things came together really well to make this kind of pencil out. And this is another thing that we kind of work through, is making sure that we give the appropriate credit for the data, not just the energy data, but considerations for the O&M and the maintenance. The steam system, like Jason mentioned, has steam traps and other things that are costly to maintain and operate and replace them. So making sure you properly account for that information can really help you move projects forward. That's what we're able to do with this life cycle cost analysis. And here you can kind of see what it looks like over that period of time, and how there's a large investment up front as we kind of deploy with that. And I guess real quick, I'll backtrack too. This didn't include the potential of tax credits of upwards of $100 million that could also be baked into this life cycle cost. So some even a cherry on top potential if they're able to utilize the credits. So going to the life cycle, as you can see, there is this initial investment that has to happen, but it's able to recapture that very quickly, and overall within 20 years, they're financially positive, and again, getting rid of that deferred maintenance. So really, going back to the principles and goals that Jason talked about, by utilizing the geo exchange, we're able to drive down natural gas consumption by, I think, approximately 90%. And be able to capture that. So really capture that waste heat. That golden opportunity, like Jason mentioned, was supposed to be focused on the only dig up once, but the railroad presented itself and we jumped on it. And then ultimately, this plan has laid out these actionable steps for them to be able to move forward, and they're seeing some of that action moving forward. So.
Yeah, so now we're kind of at this, I don't know if the word is icky, but sort of an uncomfortable point. We've had some transitions in leadership at UGA and our facilities group. We're sort of in this holding pattern for making a solid decision to move forward with this concept. Of course, tax credits are also a bit in limbo as well. So, but in the intervening time, things we can start looking at is deciding what the hot water distribution temperature would be standardized on. And it might be different depending on different parts of campus. And part of that difference will be dictated by, again, that wide spectrum of ages of buildings and building systems, where there may be buildings that, we don't even have a design standard for what is the hot water temperature in a building. But guess what? They're all 180, because that was the convention for the longest time. And so figuring out how low can you take that, especially in the peak of winter, which isn't that cold in Georgia, but can be for very brief periods of time. Can we run it at 160 and still maintain comfort control? Sitting through a lot of presentations about this at the International Districts Energy Association Campus Energy Conference, there are a lot of really good testing approaches for figuring out how much can you stretch a building like that, and then the problem areas, identifying problem areas within a building, so you don't have to try to replace all of the heating coils in the building, but maybe there might be 5 or 10% or something like that. Shift in mentality for design over the course of this study and project. We started out by getting kernels of these ideas from this process, and of course, design and construction are still continuing. We're not going to stop everything while we're studying it, especially since the architects really control that. And so, going into design meetings and saying hey, do you think you could run this building at 140 instead of 180? And in the beginning, all of the design professionals and all of our university architects were like, "What are you doing? You're going to make everything more expensive and take longer." And now we have design professionals saying "Hey, I think we could run this down to 120." I'm like, just for the record, I only asked for 140, and if making it 120 makes things bad, it's not my fault, it's yours. But we're in the process of, we do annual design and construction standards updates, and so we're drafting language to dictate what is the desired hydronic heating temperature for within buildings, and then also trying to decide what would be a theoretical distribution temperature. We're kind of circling around 160, for example. And for the record, Princeton University, which has the Tiger system, which you've probably all heard of, Ted Borer, my counterpart at Princeton, who's just retired, gave me their design construction standards for this, and it's fantastic, and I'm totally going to steal most of it to just plug into our standards. And leading into balancing the district and building interface, and so answering the questions of do we want to put a heat exchanger in the building to interface between a distributed hot water system and the building hot water system. Most of our chilled water systems just are plugged right into the chilled water distribution in a building. We only need to do water quality maintenance on one system rather than hundreds. But there may be other decisions that play there. So this is all to be worked out. And of course,
and I'll add real quick too that, I mean, as Jason mentioned, 180 has always just been the standard that everyone just kind of goes by, because it doesn't matter, right? It doesn't really affect your boiler efficiency unless you start getting to the condensing blowers, but even that's 5-10% efficiency gain. With the heat pump system, now you're starting to look at, in general, 0.5% to 1% for every degree that you go down. So that's really impactful from energy when you're talking about 180 down to 160, 140. And then you also, some of the depending on the size of the chillers, you can't get equipment that only goes but to 160 or 170, not all the way up to 180. So when you kind of switch to this electrical heat pump methodology, that temperature has a dramatic increase, in, similar to what you do with a chiller or the condenser water cooling tower reset. It's very important now versus when it was just a boiler-based system.
Yeah, and just anecdotally, talking to our O&M technicians about this, they brought up the point, like, 180-degree pipe hurts if you touch it by accident. and if you can bring that down, that'd be great for us. So it's another reason to consider it. And so we have all of these, in some cases aligning, in some cases conflicting factors at play, implementation variables, aligning new investments with the investment horizon of existing equipment, for example. And chillers are constantly getting older, right? And we can't just say like, well, just make it last longer. We've already done that. So one of the faults of UGA's O&M team is that we tend to do too good of a job of keeping things running well past their useful life, so that when it does reach a catastrophic end, it has exhausted every other option. I call it the Bluesmobile approach to capital renewal. And most people don't appreciate that, but I think it's hilarious. And campus growth is another factor. Like I mentioned, you're like, hey, do you think we have enough chill water capacity to add this dorm right here? We're like, we didn't. Okay, I guess. Like, why there? There was all these other spots that we already have extra capacity, but that's the way it's done. Funding availability, of course, as a state institution, is a huge factor. And then, of course, nobody wants to stop people walking through a certain area of campus for months at a time, but sometimes you have to do it, even for steam system replacements. One thing I'll mention is that we did recently replace steam and condensate lines, I think it was about 100 yards worth last summer, and we went in with Jacob's recommendation during the study with the same size pipes rather than small and large, just in case someday we were running hot water through that and we wouldn't have to dig it up again. All right, buckle up. Mechanical engineer talking about electrical stuff. So this is the rough map of our main campus here. The dot on the bottom is the existing substation, in case the text is a little small up there. The top one, spoiler alert, is a recommended location for a new substation. So we recently actually got the second substation in the university's capital plan, which means that is now at the state level. There's state visibility, and I'm relatively new to my director role, so I've not gone through this process before. But my leadership are like, this is a big freaking deal to get it in there. So it's really important. It'll attract funding over the next decade. Let me just jump to the next thing here. So in the intervening time, it's going to take us a while to raise the $40-ish million we need to build this second substation. And we have constraints right now. And so as I mentioned earlier, we are about to sign the paperwork to increase the capacity of the third bank at our existing substation. And what that will allow us, at least in the short term, as well as the second substation, we call it detangling the spaghetti. And so right now, we don't have enough kind of elbow room or swing space, if you're thinking about real estate, to be able to reconfigure these circuits. And so, for example, if we wanted to put in central backup generation, we would not be able to really separate out critical buildings from less critical. I'm not going to say non-critical, because every building is critical to everyone who's in it. So one of the things that we're considering, or we, the project evaluated, was a distributed energy resource program that Georgia Power recently got approved by the Public Service Commission, in which they would pay for 75% of the construction cost to put in our case, it would be about a 25 megawatt backup generator. And that would allow them to dispatch it. It would be on our property. We would own it ultimately, but they would be able to dispatch it during those 300 hours that I mentioned earlier to hopefully reduce the overall real-time price. And then we would also have it as a backup for basically half of our total capacity. And to take advantage of that, to back up those critical circuits, we need that extra capacity to reconfigure how those circuits are all aligned. I think the blue buildings stand in for red. I think we accidentally made the red buildings blue, but that's fine. So, imagine here in that top bar would be a connection to an external distributed energy resource as a backup. Yeah, anything else you want to say about that?
Yeah, no, I mean, I think it's really being able to leverage the electrical system, and it is, a single raccoon can take down a lot, right? So being able to enhance that in a meaningful way, to be able to make sure that there isn't a single point of failure or exposure to a variety of different things that could take down the campus. And, it's funny, we do a lot of work on college campuses, and, Saturday afternoon in the fall is the most critical time for a lot of people, and that outage, a raccoon coming across then would be very bad news for a lot of people. And so putting in that enhancement to reduce some of that, well, I mean, and not to discount, they do a lot of very, very important research too. So there's just all these critical facilities that you need to be able to isolate, enhance, and prioritize through these variety of different solutions that we looked at.
Oh, that gave me the time to think about the thing I wanted to say, which was we have no SCADA on our electrical system. And so when we were asked by senior administration, like, well, what are we doing, or why does a raccoon knock out a circuit for so long when at my house, I might get a blink and then the power comes back on, and we were able to explain, well, we don't have automatic transfer switches on our campus. And it's really good that we don't, because it would probably fry one of the transformers at the substation, because we don't have the capacity to allow machines to decide what circuits have capacity at the distal end when we don't have the ability to automatically switch at the substation, nor do we have the capacity to allow that to happen without human intervention. And so by expanding that capacity, both in the short term with the Bank C upgrade, as well as the long term with the new substation, we will be able to implement SCADA and automatic switching as we move forward. And so hopefully that will attract some money with being able to say, this is really good for campus resiliency. Before we say that, we should probably ask if you have any questions.
Yeah, so essentially what happens is that is a loop that can operate from 50 to 90 degrees, depending on what the season is and what the assets are, and allows that to then be serving as a condenser water for the chillers, the heat pumps, to be able to put that back and forth. So just a large condenser loop tied to geothermal, sanitary, and other things. So depending on how the chiller configuration would be, it would either be heat exchangers to allow that, and if it's like a triple bundle chiller, then it's something versus a set of heat exchangers at the plant or at the geothermal as well.
As a Georgia resident myself, and I have a lot of friends that go to UGA, but I was curious on how many times a year do you work in these buildings on campus, and do you also work in campus or buildings directly off campus?
I'm not sure I understand the
So
question.
what I was asking, so
I work every day.
yeah, no, well, I know, but there's like these projects are major projects.
Oh, I understand.
And
Yeah.
I'm assuming that these big major like energy consumptions and the like working on the chillers and heating systems aren't every day. I'm curious on how many times you all have to go in and replace these and whatnot.
Most of the time, if it needs to happen on an emergency or urgent basis during the school year, we try to make it as transparent as possible, but we do have a system of outage notifications. It's either we need to take this building down for this period of time to do this, or this building has gone down. Here's how long we expect it to, depending on the situation. But for the most part, large disruptive projects are focused on the summertime, winter break. So we have about a month in the winter. We have a couple months in the summer, especially if it involves road closures or major disruptions to campus corridors for pedestrian access. We try to keep that out of the main school year, but sometimes you can't avoid it. Can you hand it down to him?
It sounds like that $40 million was a pretty big ask. Do you think you would have gotten that had a raccoon not caused disruption?
Well, to be clear, we have not gotten it. We have simply asked for it. But the first step is to put it out there. It's kind of a woo-woo way of saying it would be, we've thrown it out to the universe, and hopefully it will come back to us over the next several years. The big ask is to get it onto our capital plan, which means that we have a commitment to do this, and then that will start to attract funding from the state and potentially even donors who want to put their name on a substation, which I don't know if anybody's ever heard of anyone doing that, but it'd be nice.
I have another question specifically about how this gets paid for. Is this done through performance contract? Is that one of the vehicles that you guys are doing, or is it just straight funding from the state?
I think we identified some of it through performance contracting. I think the important thing that we have to continue to project upwards in our leadership is that the black line, we're going to pay that anyway. Like that's what we're doing. It's the least predictable and most chaotic and most expensive option is to just not do anything other than what we currently do. And so diverting some of that into a more creative approach or modernized approach to gird ourselves for climate change, even if we don't say it that way, and for financial volatility, as you've seen with our electric costs, and we've seen it with natural gas costs as well. Water isn't as volatile, ironically, but steadily increasing in costs for us.
And one thing else, as part of that, we did have a multitude of funding sources that we had to leverage to deploy this. And for the ESBC side of things, we tried to use it for equipment, right? That has that good payback versus like piping that doesn't pay back very well. So trying to leverage those levers in the right way. So most of that's associated with the RRA. If again, the numbers that we have in here don't bank on that. That's a cherry on top, and that would be associated with the fact that it's tied to a geo exchange system, and that has significant tax credits associated with it on a capital investment, up to 40%.
When you guys are looking at your energy source, are you also looking at reducing your building loads?
Ideally, yeah. We separated this project from internal building processes intentionally because we have hundreds of buildings and it would have been it was already an expensive project, to be honest, and it would have been way more intense to try to make it a comprehensive, like inside outside energy plan. This is really just more of the systems that serve those buildings. That's also something that is kind of an ongoing process. We have a commissioning team within my department that, it's 3 people. It ought to be 30. But we have also really quickly turned the ship in operations and maintenance, who are typically work order driven rather than energy conservation driven. But both our engineering department, who does new design or manages design professionals for new systems installation, as well as our operations and maintenance people, are now singing the same refrain of what's the most efficient way to do this versus how quickly and cheaply can we do this. And that's taken, I've been at UGA since 2007, and I've watched it go from the other thing to what it is now over that period of time. In other locations that may take glacial time periods to be able to do that.
And I would add that, working with Jason's staff that I mentioned, that we didn't, try to reduce necessarily for this project the ability, but the information they provided was invaluable and very insightful. And his team, I think he's humble. They're great and provide a great source of information. And that could be a presentation on its own of what they've been able to accomplish in a few years.
Yes. Were you able to price in any intangibles like renewable energy credits or anything like that? Maybe the importance of renewables for a university facility?
I can speak to that. In Georgia, aside from having enough, say, solar generation to meet the needs of a REC aggregator, the RECs have absolutely no financial value to us at all. We have no state level or even university level mandate to increase renewables or decrease carbon emissions, and so it's really that is not a high priority for the state. It is for me, but yeah, it wasn't a major factor in this.
Yeah, I think it's setting up for that, assuming future greening of the grid. So by the time this is done in 2040, 2045, hopefully the grid is a little greener and getting that way.
So in one of your earlier slides, you mentioned that I think something like 50% of the utility cost was in so many, like 40 hours or 80 hours, whatever that number was. So it was a little bit surprising to see that thermal energy storage wasn't one of the measures that was considered, especially given that IRA, was going to pay for up to 40% of that. So is that something you guys looked at, and was it ruled out for a particular reason? I asked because I just tried to do a 3 million gallon tank for university, and ultimately optics came down to why they didn't want to do it, even though it was an immediate payback.
So you're right, and some of the, I guess a couple of things that we saw was some of the benefits of the kind of, say, slosh in the system because of how it was going, that kind of inherent thermal or inertia. We did also look at TES, and it did make sense from a financial, didn't make sense from a location perspective. There was very tight spaces in UGA so we couldn't really fit it next to the depth locations we identified. And
we've studied thermal energy storage in the past. It was not ice storage; it was just chilled water storage, and that was, all of these bodies of work or this body of work of past studies, some of which Jacobs had done in the past. I don't know if you guys did that one. It came down to back then. It was long enough ago that we didn't see this kind of spikes. But the economics now are much different than it was, but it comes down to space. The nice thing about the geo-exchange field is that you can still use the land on top of it. In fact, from the planner's perspective, putting an asset like that in a green space preserves it as green space forever, or for the life of the project, which is, in my case forever. Um, if we were storing ice, that'd be a different story. But we don't want to make ice. We don't have technicians who are interested in doing that. And we don't have, we do have a lot of poultry processing where there are folks who work on ammonia systems and things like that, but we just really aren't interested in bringing that to campus. Chase, you got any questions about Steam? Well, yes, for the most part, where we can. One of, like I said, I came to UGA 2007. My first 7 years, I was doing energy audits on and off campus as kind of more of a service role. And one of my kind of unicorn projects was a building that was still on pneumatics. And it was right a couple of years after they had installed their first steam meters. And I was doing this work for the person who had my office back then. And so he said, can you figure out why this building's using the same amount of steam in August as it is in January? And it turns out the outdoor air reset tube had been pulled out of the port that was supposed to set the temperature down to like 140 in the summertime. This is a building from the 60s with multi-zone air handlers in it. But yeah, in general, we do that. And so most of the time, or, outside of the deep winter of Georgia, we really are running at like 160. At least that's what they tell me. Well, thank you. Oh, we got one more. Yeah, so we have some buildings that have chiller plants in them that are districted. We have very few that are on main campus that you see here that are standalone, like entirely standalone. Some of those buildings have really great chiller rooms. Like even if the chillers were to go away, we would put chillers back into those places. That's like 3 or 4 buildings. The rest of them, the chillers and the other equipment are like shoehorned in there. They seem to have built the buildings around it or whatever. And it's like, how would you even get a new one in here is the question. And they're cramped. There's sort of this weird period of time where they gave us, some chiller plant rooms, you could play hockey in there, and other ones, even now we're in design for a new medical school building, and it's a really fast track project, and they've already designed the envelope and have eliminated a number of different chiller manufacturers because they've already run out of space in the mechanical room. They're like, what if we chose this kind instead? And like, nope, can't do it. Boom, they're gonna hit each other. So that building will be standalone because it's on a separate campus from this one. But
One thing I'd add too, and you've talked about it before, is the stakeholder involvement too, of like when you hear the facilities master planners talking about district energy plants and thinking about that and getting that kind of educating them and getting them thinking about those things to ease that transition so they understand it and not just think it's a pain in them. It's an enabler instead of a problem.
Yeah, it comes down to real estate though, and we're having these hard conversations about, what we really like, it would be ideal to put this DEP here. Well, we were planning to put a research building there, and we have to ask, like, well, how do you plan to heat, cool, and provide electricity to that? Well, can you put it over in this weird triangular lot where there's a bunch of rock? Like, I guess, and that's how many of most of our district energy plant, or well, not most, we have 2, but our district energy plants, and then we have some anchor chillers that are, not a plant, because it's one chiller, but it's kind of built separate from a building, have very odd shapes. Like one of them is very long because it's between a road and a stream, and it couldn't have been 1 inch closer to the stream. And there's not enough room to expand it lengthwise either. Another one is, between a building and our steam plant, and so it's going to eventually sort of creep into and bump up against the end of our steam plant, and then that's could be beneficial in the future if we're trying to combine these systems, but or cross them over. But yeah, I mean, convincing the folks who make campus beautiful that we need to build this thing they don't think is beautiful in a place where they want something beautiful is really the hard part. The math's easy.
The math is easy. It's the people that's hard, right?
I think we are done with the presentation, and I'd like to thank our presenter for a small gesture, a token of appreciation for your time and teaching us.
Thank you very much.
Thank
Appreciate
you.
it. Thanks, everybody.
Thank you guys.